All right, welcome to the Asteroids and Comet session. Just a reminder, talks are 15 minutes.
Thank you for coming to the last session.
Thank you for dancing with us till the end. Talks are 15 minutes, 12 minutes for the talk, 3 minutes for questions. We will have a discussion period at the end, and then we will go back to the main hall for the keynote speaker and the wrap-up. So with that, we'd like to welcome the first speaker, who is Norbert Schorghofer. My last name should not convince anyone that I can pronounce German last names.
Thank you. So does this microphone work? Yeah. So this asks, does these microphones work, right? This asks the question: can we expect a near-Earth object to still have ice in its deep interior or somewhere, or rather, what are the conditions? What's favorable for them to still contain ice or not contain ice? And the motivation, or at least part of the motivation, or number of motivations. I have two pointers here. Okay, are listed here, and of course, I don't have to tell this audience that one of the reasons we're interested in ice and near-Earth objects, which are much more reachable than asteroids in general, is to mine them. And this is not to prefer one company over the other, but this is just a beautiful illustration of asteroid mining. And so what I'm trying to do here is put a quantitative handle on how fast does such an object really lose its ice. And by lose, I mean through vapor diffusion, through all the regolith it has to go through, so ice to vapor to space. So what are good numbers for these timescales? And so how does one approach such a problem which has many unknown input parameters, right? How does one get a sensible answer with many unknowns, which is a very common situation in planetary science? And the answer to that is a parameter sensitivity test. So one tries through a large number of parameters and finds out which are actually the most important, and focus on those, and accepts that many others are not known. And here's a result of one such parameter sensitivity study, and this is for ice buried about 1 meter. Delta C is a burial depth, and this is 5 meter, as a function of temperature. So the warmer it is, the higher the vapor pressure, more gets lost, and this is a loss rate. And there's various graphs and various parameters for overlying layers, different porosities, different particle diameters, which matter because the mean free path of this particle changes. And the answer is that it's very temperature sensitive. So this is intentionally a linear plot. So no matter, so to speak, or barely matters what your other parameters are, but temperatures need to be below about 150, 140 Kelvin. Otherwise, not be able to retain ice in a top few meters. So for example, if we talk about Phobos, is there a chance that a neutron spectrometer that goes to Phobos will see detect ice? And also talk about macroscopic ice, not hydration. And the answer is no. So this is a sort of the effective temperature of Phobos. This is somebody calculated sort of a minimum temperature on the surface. So the 170 Kelvin, it's hard to find any material properties, surface layer properties, which would allow that. So I expect there'll be no macroscopic ice be detected on Phobos for that reason. So the answer is one has to focus. One needs accurate temperatures. That's really necessary to estimate any ice loss rates. And so therefore I really focus on temperature modeling. And so for the deep interior, not near the surface now, but for the deep interior, this is a basic thought that this temperature at the center of the body is the same as the temperature averaged over the surface, area averaged, and averaged over the orbit, of course, because in the interior the temperature won't change. And this is the formal argument that accompanies that, that the heat flux integrated over any surface must be the same. There's no internal heat here. And so we are really interested in the temperature averaged over the surface, which is always less than the effective temperature, by the way, because the effective temperature, all the incoming sunlight gets radiated uniformly, is sort of a minimum radiation. minimizes T to the 4th. So for example, if you have a fast rotator without axis tilt, your average surface temperature, area average surface temperature, I call it T bar, is 1% less than the effective temperature. And so, you know, in a one-dimensional sort of spherical model, this at least have now reduced the problem to finding one temperature, T bar, the area average temperature. And this is, I'm not showing the calculation here, which is some paper which is on a preprint archive, but only the result. So this is a time scale, the time it takes for the eyes to be completely lost from a body at all depths. I call it TD. R is a radius of a body. D is a vapor diffusivity, which depends primarily on, you know, the pore sizes, which, you know, for NEO are, you know, we don't know, but maybe a centimeter is a typical number, and it's just a ratio of ice density to vapor density. If you had a planar slab, this would just be 2 instead of 6. It's not that different. So I can estimate these time scales. This is another result. This is actually a fully analytic solution. This is, you know, this is a spherically averaged, you know, solution, one-dimensional solution, but there's actually an analytic solution. Well, the advantage of being an analytic solution is you know, you can apply it for a wide range of temperatures and scales and radii and so on. So this is normalized by radius. This is normalized by desiccation time TD. This is a cube of the you know, Ri is the size, so to speak, of the remaining eyes. And so after 11% of that time, it turns out you lose half of the eyes. So this TD is you use all of your eyes in an order of magnitude. 11% of that TD is you lose half of your eyes volumetrically. And you know, one gets these beautiful, simple solutions, which make a problem the answer very transparent. But of course, the interest in actual numbers. So here I first show this as a function of average surface temperature, desiccation time. So this is the age of a solar system. This is a desiccation time. So you know, it tells us if you want to last the age of a solar system, you know, and you are at say 160 Kelvin or so, you need diameters of a few kilometers, for example. And this now assumes a mean free path of a centimeter, right? That's an assumption, but all these times are now proportional to this mean free path. But we really like to see this as a function of semi-major axis, I suppose, rather than average surface temperature. But the average surface temperature, of course, is a function of more than a semi-major axis. I mean, a semi-major axis dependence, you know, must be something like this. Perihelion distance doesn't matter much, right? For the interior of a body, it doesn't feel, you know, this seasonal variations don't go very deep. So this is now the average surface temperature with T bar from numerical thermal model calculations. And one quantity which is hugely important, if it's low, is thermal inertia. So very low thermal inertia, Sirius, for example, is very low thermal inertia. These bodies are much cooler, and that's the reason why Sirius still has shallow eyes, okay, and still hold on to shallow eyes. And you know, it depends on axis tilt. So the dotted here will be effective temperature, and so it turns out this, the fast rotator with zero axis tilt is sort of a upper limit to any realistic temperatures, and that's what I will assume. So it's a conservative estimate of what's happening. So with low thermal inertia, you get much cooler bodies, therefore longer desiccation times, and higher axis tilt also makes cooler bodies. And so with this very sort of pessimistic estimate of the temperatures, I can plot this as a function of semi-major axis. So let's say 2.8 AU is sort of the beginning of the outer asteroid belt. You know, what body do you need to last through the age of a solar system? For ice, if it had ice to begin with, of course, you know, what size of a body do you need to last? So it's between the green and the red line. So, you know, a few kilometers sized body in the outer asteroid belt was able to retain ice over the age of a solar system. So it's sort of a quantitative answer. Now, some NEOs come from the asteroid belt, from the outer asteroid belt. And here I pulled down just a few days ago the statistics from the JPL, study at JPL. And there are, you know, almost 900 bodies known which are larger than 1 kilometer. So 10 kilometer, you know, I don't think we could expect that. And so a realistic scenario is you have a body larger than 10 kilometers outer belt, and that will be able to retain its ice over its entire age. It will experience a breakup, and then a smaller body, much younger, smaller body, you might become an NEO and pass near Earth and be mineable or reachable. And so for example, if that breakup body is 100 meters, you can allow about 2 million years. So it's you have 2 million years before that is desiccated too. And again, this is the pessimistic case of high thermal inertia, low axis tilt. There are ways of making this cooler. And so estimate is 8% of NEOs come from the outer belt. I haven't calculated a fraction yet of NEOs, which you can expect it to retain ice. It's a small fraction, but one needs to put in more statistical information about the orbits of NEOs, which we haven't done yet. And so then there's another interesting aspect to the story, and that comes out of another sort of solution. One can actually, I'm skipping the math here. This is what the interior temperature field looks like. This is a cross-section of a body with zero axis tilt, fast rotator, a surface boundary condition. And of course, if zero axis tilt or even with small axis tilts, your poles are very, very cold. And again, because the sublimation loss is so sensitive to temperature, this makes a huge difference in ice retreat. So this is, the white lines is as the ice retreats, at equated retreats faster, but at the poles are just so cold in this particular example. So if you go mine an asteroid, if you want to find near-surface ice, the rotational poles would be a good place to look at. Of course, we need to have a stable axis orientation. If we wobble around, that would no longer be the case. But that's the first place I would look at to find shallow ice. So these are sort of, I think I can now systematically list the factors which favor ice in the deep interior of NEOs. Sort of semi-quantitatively, you need a semi-major axis on the outer belt. So NEO can still have a very large semi-major axis, right? And because otherwise a parent body would have to be more than 10 kilometers, and there is not that many of them. So sort of the outer, so only outer belt and beyond can we talk about bodies smaller than 10 kilometers. A parent body is smaller than 10 kilometers. And then, of course, the what's probably a breakup product, would have a young age. It's understood. It's not quantified here, but we talk about millions. Well, it depends on the size, right? And this is very the small particle size comes in. Dust layers make bodies much cooler, right? So this dust covers retain ice. Just for temperature reason, and on top of that, the vapor diffusion is slower because the main free path is slow. So dust-covered bodies have a much better chance to contain ice. And I look at the polar regions. And I guess I'm over time, so I'll just leave up the summary here. Thank you.
We have time for a couple questions. Okay, let's start with Melissa. Wait for the mic. Sorry, so people online can hear you.
Okay, thanks. So you've mentioned that the dust is, you mentioned that it lowers the surface temperatures, but it's also low thermal inertia, so it can heat up very quickly too. So maybe the point is really that it's more insulating rather than it lowers temperatures, right? Or am I missing something there?
Yeah, so the line of argument is because it gets hot at daytime, it radiates more. And therefore, deep down, the mean temperature is lower. So the bigger the amplitude, so the lower thermal inertia, the higher the surface temperature amplitude. Therefore, the average of T4 is higher, so it radiates more because it insulates so well. Yeah, that's the line of argument. So, yeah.
This is a question kind of intersecting science and resource utilization. And we were in Luxembourg a couple of months ago. And we were discussing our interest in looking for ice in the poles of Bennu and Ryugu. And Joe Sercel said, you scientists, that's not enough for us to be bothered with. But if we were to detect ice in the poles of one of these asteroids, I'm sure that most of the industries that eventually are going to want to mine much larger quantities are going to want to use that as a site. But what do you So you think that if in the case of these two objects which have low obliquities, that we have some chance of finding a little bit of ice in these two specific objects?
Well, it critically depends how old they are, which is most cases only know statistically. So, well, somebody knows this better than me of what the age estimates for these bodies are. So, but it's, in some cases, because we most often don't know the age of a body, meaning particularly the time it has been in this orbit, it's hard to do it for a body individually.
Yes.
But if one does know, I mean, the more one knows, the better.
Yeah, we will know roughly statistically what the chances are of them having been closer or further from the sun. But
Yeah, so at this point, I think I don't dare to say this for these individual bodies. Yeah.
All right. Well, let's thank our speaker. Our next speaker is